Yeah, thanks. Okay, yeah, thanks to all the organizers for inviting me. I haven't seen much of Florence yet, but I'll be here over the weekend, and I heard it's pretty, so let's see. Hopefully no rain. Um, Okay, so yeah, I'm going to talk about more, let's say, traditional approach to galaxy clustering. So in contrast to what Beatrice has been talking about, where we do the simulation-based inference, et cetera, et cetera. I'm just going to be talking about regular, computing summary statistics to get cosmological information from large-scale structure. Um, no. Uh, but I just exited the Zoom call. I'm out. When I pressed the button, I left. Don't worry. Should I just join again? No. Maybe I could just use the. Yeah, no worries. Also, I think my internet is kind of. See. Yeah, it keeps logging me off of the Educom for some reason. So it's like I don't really know what's going on. Yeah, yeah. Oh, good. This one, please. Um, okay, I'm just gonna press the button. Yeah, sure. So now the recording starts again, or how do you want to? Uh, oh no, no, I shouldn't unmute. Yeah, yeah, yeah. Yeah. Okay, so I'm gonna put this here. Okay, let's try again. Yeah, so I already more or less introduced myself. I'm a PhD with Elisa Kisari in Utrecht. She's also going to be here next week. And yeah, I work on large scale structure in general, but mostly perturbation theory. So the sort of mandatory introductory slide, right? We have lots of data from many different large scale structure surveys. There's DESI currently operating. Euclid is also actually collecting data right now. Spherix has been launched, and then there's a few more in the pipeline. And I'm going to be focusing on the spectroscopic galaxy clustering side, right? Just like pretty much everyone in this workshop does. So we have powerful three-dimensional statistics of galaxy clustering, and we can use that to perform tests of the lambda CDM concordance model and possibly or quite likely even extensions thereof, right? So maybe some extended dark matter models, maybe some interactions in the dark sector, et cetera, we can probe this. So the way we do this from galaxy clustering is we can we can probe both the expansion history via baryon acoustic oscillation measurements, and we can also probe, well, traditionally the growth rate from the shape of the galaxy power spectrum from the redshift space distortions. Then lately, let's say over the past decade or so, there's been this this program that wants to use the full scale dependence of the galaxy endpoint statistics, mainly the power spectrum, but also the bispectrum, to get really all the possible information from this data, sort of in analogy to the CMB, right? Where we don't just extract features of where are the peaks of these baryon acoustic oscillations, but we want to know actually the full scale dependence of the TT and EE angular power spectra and so on. So when you want to use the information from the scale dependence, well, we can do this sort of full shape approach, which has been applied to BOS data by numerous groups. There are also other ways to use information from the scale dependence of the power spectrum, like this this shape fit approach, which just extracts in a maybe less model dependent way some features from the power spectrum. But I will not talk about that. Okay, so I mean, what we measure traditionally, again, is just correlations between pairs and triplets of galaxies, right? And then maybe in Fourier space or not. So we measure, for example, here is some data from the DESI collaboration. We can measure the monopole and quadrupole of the galaxy power spectrum in redshift space. Maybe more ambitiously, we can also try the bispectrum, which is not shown here, but this is also detected very significantly in DESI data. And then we can go on and on, depending on how brave we are, depending on how much labor we put in. We can also detect higher order endpoint statistics. Like I think recently there was also a paper that detects the that detects the galaxy trispectrum in DESI data. Okay, so again, in similar spirit to the rest of the talks, we do perturbation theory for large-scale structure, which basically means that our observable, which is the galaxy density field, we expand in this galaxy bias expansion, which, okay, colloquially speaking, is just a Taylor expansion in the dark matter overdensity, with some caveats and details that I don't want to reiterate too much. But of course, we have to obey the symmetries that the galaxy density field should obey, like Galilean symmetry and rotational invariance and so on and so forth. So if you do that, then you can just write down order by order what contributions you will have in the galaxy density field, order by order in the dark matter density field, right? So fundamentally, the idea is that galaxies, they form from the dark matter overdensity, and therefore, yeah, given, let's say, the dark matter field in some region of space, I should be able to predict what the galaxy density field should be, at least statistically, right? Okay, so then there's also all these free parameters. So these bias parameters, we don't know what they are. They're not predicted by EFT. We could go and measure them, or we could use simulations to better constrain them. But in principle, they're not predicted within the theory, right? We just don't know how galaxies form, and so we have to treat them as nuisance parameters. Okay. So then what is currently the state of the art is that people compute the galaxy power spectrum at next to leading order, right? So what you do is you take your set of cosmological parameters like H0, omega matter, sigma 8, and maybe some other things, and then you compute these correlation functions of galaxies or power spectra. And this means that, as you go to higher and higher order, you can include more and more scales in the analysis, and that will give you better constraints. So the one loop power spectrum specifically has these two different contributions that you need to compute. So two different ways in which modes can couple at one loop order, which are these P22 and P13 diagrams. And this is something that has been implemented in many public codes by now, right? So we have class PT, we have class one loop, I don't know, velociraptors, PyBird, PBJ, Comet, really many people, many different groups have implemented this. And then when you compare this to the Galaxy Power Spectrum data, you get a few percent constraints on lambda CDM parameters like H0, omega matter, and sigma 8. And just for future reference, when you write down the Galaxy bias expansion at this order and you compute specifically the power spectrum, right? So as we already discussed, there are degeneracies at the field level in this bias expansion. But if you just want to compute the power spectrum at next to leading order, you end up with 10 parameters or so, depending on your modeling choices. Right. Then the next thing that people did, which is not something that DESI did, for example, is compute the one loop bispectrum. So this is fourth order in the density field. This is already much more complicated, not just because you have to go to fourth order in perturbation theory, but also because many of the degeneracies that you have at the level of the power spectrum, they are no longer there at the level of the bispectrum. So even at third order, for example, you already have more contributions in the bispectrum than you have in the power spectrum, just because of the fact that you have more external momenta now. So this was carried out in a number of different papers. So there's a paper by Oliver Wilcox, and there's also the group by, well, there's Leonardo Senatore, Guido, and Pierre as well. Basically they applied this to BOS data, right? One has to compute all these different contributions at the one loop order, and the result that they obtained was that you can get, let's say, a 30% error bar reduction on sigma 8. So here in this corner plot, you can see the comparison to Planck, and you can also see the comparison to just doing a power spectrum analysis. Right, so in gray you have just the power spectrum, and then in red you have also the bispectrum at next to leading order, and you see, okay, this contour seems to shrink a little bit, and constraints, in particular on omega matter, are quite competitive with the CMB, so that's nice. The other parameters, they don't really improve so much in the one loop bispectrum in this setup at least. So I'm going to compare it to what we got in a recent reanalysis, not on BOS data, but on some other data. Here you have many extra free parameters, right? So if you do the one loop bispectrum consistently in this EFT approach, you get, let's say, order 40 extra parameters if you really include all the redshift space counter terms and so on and so on. But also this bispectrum data vector is large, and you get hundreds of extra data points. And so in the end, well, when you add those up, then, you know, at the bottom of the line, you get some 10%, well, tens of percent improvements on cosmological parameters. Okay. Also, what's kind of important here is that actually the likelihood is not so complex if you are happy with putting Gaussian priors on these nuisance parameters, and if you're also happy assuming that the likelihood is Gaussian. And why is that? It's because, well, you can just marginalize analytically over all the parameters that occur linearly in the whole model, which in the case of the one loop power spectrum and bispectrum would be all of the third and fourth order contributions, and also all of the counter terms, they're always linear, right? So yeah, if you just put some Gaussian prior with a width that you're happy with, then you can reduce the complexity by quite a lot already, and maybe the parameters that you have to sample explicitly. There's maybe like, I don't know, 5 or so per redshift bin. So this is actually manageable. Okay, but the main challenge that I want to address in this talk is how you actually do this inference, because this is not easy. In particular for the one loop bispectrum, but also I will talk a bit later about the two loop power spectrum. So to run this analysis, you have to render it practically feasible in some MCMC setup. So you would like to evaluate this one loop bispectrum in, I mean, ideally way less than 1 second. Of course, if you can do it in 1 second or 5 seconds, you will also get constraints. But you know, if you sort of think ahead where maybe, okay, I have this full shape likelihood and I want to combine with something else like the 3x2 point, et cetera, I mean, this gets very big and very cumbersome very quickly, right? So you should not just stop when you've managed to run the chain for just the full shape likelihood. So these theory predictions, they're difficult, right? Because in cosmology, in contrast to particle physics, we don't have a simple form for the propagator in these loop diagrams, because the propagator is the linear power spectrum. And the linear power spectrum we can only obtain by solving some relatively complicated set of linear differential equations. And that means that there's no closed form for this, right? It's just some complicated function of scale. There's the initial power spectrum, which is, okay, a power law, presumably. There's no scale, but then all the physics imprints a lot of scales on this power spectrum, right? We have the turnover scale and then some BAO, et cetera, et cetera. So these loop integrals, they look like some functions of momenta, which are these F kernels, and then some instances of the linear power spectra also evaluated for the internal momenta that you have in the loop. And this linear power spectrum also has a pretty large dynamical range, right? So on very large scales, I will have this power law, but then at k of 10 to the minus 2, there are some interesting things, and at k of 10 to the minus 1, there's also interesting things, and at k of 1, et cetera, et cetera. And these are high dimensional integrals, right? So I would like to compute some high dimensional integral in, well, milliseconds, preferably. Okay. So then what did people do? Well, the first thing that you notice is that at least in the standard setup where you just write this galaxy bias expansion and you use the EDS approximation and so on and so forth, the cosmology dependence in this loop integral is only through the linear power spectrum. And so then what you say is, well, this loop is somehow like a multilinear function with all these power spectra. So if I somehow manage to decompose this power spectrum into some weights, which are these W of theta, and then some functions V of K, then actually, if I plug that in, so I have this bilinear there, I plug it into the loop and I can just pull out all of the W's and compute only once the integral over all of these different basis functions. So that basically my, let's say, L loop computation becomes just a sequence of matrix multiplications, basically, right? So for linear theory, there would just be some linear, some dot product of these weights. And then at quadratic order, there will be some, well, rank 2 matrix multiplication, and then rank 3, 4, et cetera, right? So again, the point is that this pre-computation you only do once, because these, well, if you have an expression like that for bilinear, then V doesn't depend on cosmology, right? So if I want to now recompute it again, recompute the loop again, then I would just recompute the weights and then pre-compute, multiply by this pre-computed, well, matrix or tensor S. So because you do it only once, it doesn't matter. It doesn't matter if it's done numerically. Many people have looked for ways of doing it analytically. Of course, if you can do this, that's nice, but you only have to do it once, so it doesn't matter if you do it numerically. Yeah, if you're happy doing it numerically, then it also just gives you something that works for any endpoint function at any order. So you just pre-compute some of these small matrices or tensors, and then yeah, be on your way with the loop calculation. Does it make sense up to this point? Okay. So yeah, for example, some of the decompositions that have occurred that do this analytically are just FFTs, right? Where you decompose the power spectrum in some power laws, and then maybe for these power laws you can do the integrals analytically, and then also Leonardo's group devised a method that uses some other set of basis functions for which you can compute at least the one loop bispectrum also analytically in terms of some master integrals. I don't want to go too much into that, but yeah, that was kind of the state. Okay, so I mean the point here is that I mean it's really a very simple thing, but as we will see, it works quite well. So if you're happy doing these integrals numerically, then what is the best possible way to choose these functions? I mean, it doesn't matter if I have some formula for these functions. All I need to know is I want to have as little as possible because then my likelihood will be as fast as possible. So I essentially want to have a decomposition for this linear power spectrum, which minimizes the error for a given number of basis functions. So let's say I want to find the best 10 basis functions. How do I do that? And that's, you know, from a, let's say, numerical mathematics point of view, numerical linear algebra, this is a very straightforward problem. So what you just do is you say, okay, the linear power spectrum, I roughly know what it looks like. So implicitly, you specify some prior on cosmological parameters. Then linear power spectra, they all look more or less like, let's say, the Planck power spectrum, and then some residuals. And then if I use, let's say, a grid in cosmological parameters, where these cosmological parameters are my prior, and then I use some wave number templates, then I can put all of those into a matrix. So that's this PL of Km. And then all you have to do for this SVD is just do rank compression on this matrix. Just one small technical detail, as usual with these PCA or SVD type methods, it's nice to normalize your data so that, you know, where the power spectrum is large or where the power spectrum is small, you would like to get the same relative error. So that means it's nice to normalize the data. Again, you are free to do this as long as you just perform linear operations on the power spectrum before doing the SVD, because I would like to preserve the linearity. Okay, so this PL theta, yeah. So the dimensions are the wave number grid. That's one dimension, and the other one is just all of the templates that you put in. So you know, for 10 cosmological parameters, it's also just one because you just stack all of them. Yeah, yeah. Right. So that's the dimensions of the matrix. And then this SVD, it basically just finds vectors. If you want to be very concrete mathematically, just finds vectors such that projection into that subspace yields the minimal mean square error. So this is really optimal in, you know, a very precise sense. And so you really will get the best possible choice for these basis functions. And by the way, doing this SVD, like if I have maybe 10,000 templates and let's say 500 wave number bins, I can just do it on my laptop. I just press enter. This is linear in the number of NB that I choose, and it will just run in like I don't know, few seconds or something. If you make it really large, if you need more memory, okay, then you run it somewhere else, but this is a very cheap thing to do. So yeah, I do this SVD, and then I will just get these basis functions, V. So the V hat that you get out of the SVD, those you have to then sort of scale back with this rescaling that you did. And the V hat, they are automatically orthogonalized, right? So once you project into the best one-dimensional subspace, then it will just find, the next basis vector orthogonally to the previous one, and so on and so forth. Which means that it's very easy to obtain these weights, right? So if I want to know what these weights are, I just need to compute for a given power spectrum. I need to divide again by this p bar and then just project orthogonally with this basis. Okay. So then, well, what do you get in the end? So it turns out that if you do this, well, because we already know more or less, right, within the priors that we have, that power spectra look very, very similar, right? They all look more or less like Planck. They go up, then they go down, and then there's some wiggles. So this power spectrum across reasonable priors is a very compressible thing. So here you see in some plots what you get for these components. So basically this V1 component, this basically looks like Planck. So maybe if you think back to Matt's talk, where they had this idea of expanding around Planck power spectrum, well, this is basically like that, right? So the first vector that you recover, the first principal vector, basically looks like Planck power spectrum, and then the other ones are sort of the best possible way to model the residuals, right? Whereas with them, the residuals were modeled in some other, let's say, semi-analytical sense. So what you can see in the plot is that when you go to higher and higher basis functions, so V2 or V3, etc., the broadband gets more complicated. This is expected, right? Because these things are supposed to be sort of orthogonal. And they also need to capture the wiggles around BAO scale. So yeah, they do that by having sort of ever higher frequencies, if you like. Right. Then what I also overplotted here in pink is this the smoothing. So this is what you need to do if you want to evaluate theory prediction. We would like to take into account the effect of the large scale displacements in Eulerian perturbation theory. This is done via this wiggle no wiggle split. And the nice thing about choosing a suitable prescription for this wiggle no wiggle split is that you can get this smoothed version of the power spectrum by just applying the smoothing on every basis function individually. This is true if the smoothing procedure that you apply doesn't depend on cosmology. Otherwise, I would break it. But yeah, I think it's very reasonable to assume that you can choose this wiggle no wiggle split procedure to be independent of cosmology. Here's one example from a paper by Zvonimir Vla that basically divides the power spectrum by some fiducial curve, like this Eisenstein-Huth thing, and then you smooth with a filter that depends on the scale, but not on the cosmology, right? So those are the pink curves then in the end. And so you don't have to think, for example, for this V7, you don't have to think about, oh, well, is this, is that little thing on the left, is that part of the broadband or the wiggle or not? You should just apply the filter, and then you will preserve the total power spectrum sort of by construction. Okay. Yeah, so as I alluded to before, these higher basis functions, so everything you get beyond V1, this rapidly decreases in importance. So if you plot, for example, the singular values as a function of the index, so I, right, I as in VI, then you see that the first one is large, and then right, so sort of comparable to the amplitude of the power spectrum, and then the other ones, they're smaller, right? So they're less important. I also put here some examples of the ranges that we chose when we generated this grid, and then we did this SVD and so on and so forth. So you can see, for example, that for lambda CDM, which is the top table, then even if we make the ranges quite broad, like this this left column where you take omega C between 0.08 and 0.18, even then you get like, for example, in the that's the pink line, right? So even there, like with 13 or so basis functions, you're already almost four orders of magnitude below the first singular value. So yeah, if you check how accurate this decomposition is, which I will do in a minute, then you will see that it works very well. We also did this for extended cosmologies just to kind of see what happens. So if you include like neutrinos or W naught or WA or curvature, you vary the redshift, et cetera, it all doesn't really matter. Of course, the number of basis functions that you need for a given accuracy goes up, but I mean, you're really, you're never looking at more than, let's say, 15 if you want per mil precision. So yeah, I think this is very reassuring. Okay, so then, yeah, just yeah, go ahead. Right, so it's I mean, when you do this singular value, I mean, this matrix sigma, right, that you get in the singular value decomposition, this is diagonal, and the values on the diagonal, those are, so yeah, they're singular values, not really eigenvalues, but yeah, I get, um, yeah. So when you then decompose the linear power spectrum, so here's some plot for some ranges that we tried. They're from the previous slide. So if you do this wide lambda CDM thing, then you see that if I use, for example, 13 functions, which is the green line, then I get to below per mil, right? The error is in percent. And then I can just make it go down further and further if I want to. I can do 0.01% if I want to. And so these pink lines, they represent the 3 sigma percentile of, you know, if you would sample this whole parameter space again, and then you would see how well are these power spectra recovered by truncating the singular value decomposition. Then yeah, 99.7% of them would be below 0.1% for NS13, for example. So this is like an emulation error or an emulator error plot, if you like. I hope that makes sense. And then for the larger parameter space, you need more basis functions, but okay. Or actually, well, so the number of basis functions that you need is more sensitive to omega C, for example. So for omega C, if you make that narrower again, as in the right, then you actually need nominally less basis functions. So these are just some numerical things that we investigated, but yeah, the overall conclusions are really the same. You never need more than 15 of these things in practice. Exactly. Yes, that's what I'm saying. Yeah. So the number of, yeah, so you had these grid numbers. Yeah. Oh, I think I forgot to mention that, but yeah, so you make this SVD grid, right? And yeah, you can fix some of the parameters because yeah. Yeah, exactly. So yeah, the total size of this SVD matrix would for the bottom right would be 30 times 12 times 12, right? That's the whole. So that's a big one. I don't do it on my laptop. Yeah, and some parameters you can fix because you think, you know, they won't influence the K dependence so very much. So yeah, okay. Right. So I was saying, where was I going? Right. So these things, they can be yeah, you only need 14 or so, or some amount like that. Essentially because the shape of the power spectrum is very similar across all the templates, so you converge very quickly. The reason why we made so many of these templates is just to make sure that you don't have any sort of undersampling or resolution errors, right? You would really like to get the best possible guess for this V of k, which, you know, if I only take 2 grid points, then there's going to be some sampling error, right? If you, yeah. But yeah, getting all this to converge really was not difficult. Okay, so then if you do that, you can do you can evaluate the linear power spectrum in 250 evaluations or so. Sorry, 250 in a few milliseconds. There are other codes that can do this as well, right? Yeah, so this all works very well, and that's also partly because of what I want to explain next. I think I am going to ask, how much time do I have just for reference? Oh, okay. Yeah, well then I think I'm gonna skip this. Um yeah, okay, understood. I don't want to keep people from their meal. Okay, so yeah, let me maybe then just skip this bit. So all I will say is that these weights W, of course, you can compute them again once you know, you can call class and then do this orthogonal projection with your fixed set of functions, and then you can compute the weights, but you can also emulate the weights because they're just functions of cosmology now, right? So you can emulate them. We emulated them with some radial basis function related technique. I'm going to skip it, but the point is that that error is mostly negligible compared to the error that you get from truncating this NB, right? So all you can see is that, for example, for this NB equal 14 case in the bottom panel, there, I mean, it's plateauing because this is the emulation error kicking in. But yeah, other than that, you know, it just kind of is going down. And okay, if you want to go beyond this pink line, then you should really just build a better emulator. But okay, you're already below 0.1%. So yeah. Okay, so then I skip that. So now if you have this basis, you can also compute immediately the galaxy power spectrum at next to leading order. And you will get 10 to the minus 4 or so precision. It'll be much faster than FFT codes because now these matrix multiplications, they're much smaller. And here you can see for some instances like how we did this. So the middle row is for this default lambda CDM. So, well, still reasonable priors. And then if you make them wider, okay, you have to use more basis functions, but this error is extremely small. Okay. Okay, but the galaxy power spectrum, I mean, again, there are many codes that already do this, so this is not really what it's made for. It was made for the galaxy bispectrum at next to leading order, and also the galaxy power spectrum, sorry, the dark matter power spectrum at next to leading order, which I will also talk about later. So yeah, if we have this basis decomposition, we can also just reanalyze the PT challenge data for the bispectrum. So this is the redshift space bispectrum multipoles, where we want to consistently vary all cosmological parameters, right? So this is something that was not possible with FFT log because you need too many frequencies and you run into memory errors, you run into memory issues, and also this this method that Pierre and collaborators used on the BOSS data, well, at least requires more basis functions than we needed here. So if you use, for example, right, if we use NB equals 8, so this is just again for lambda CDM, right? We're not varying anything other than H0 omega matter and sigma 8. And you can see that if we use 8 of these functions and we include really all the relevant observational effects, right? So we have Albert-Paczynski distortions. We also do IR summation in the loops. And then you can see that if you use 8 basis functions, so in the top panel, I mean, the error in the total, you know, 3 plus 1 loop bispectrum, this is very, very small for the monopole and then a little bit larger for the quadrupole and the hexadecapole. And for the total PT challenge volume, which is huge, right? Like 500 gigaparsec, you can actually stay below 0.1 sigma in this computational, let's say, emulation error. Yeah, yeah. No, on like part by part. So yeah, the Alko-Purchinski is by Taylor expansion. So you can still, yeah, you just Taylor expand in omega matter basically, and then you have all the different contributions that you can integrate term by term for the multipoles. Um, yeah, so that's another thing, right? So you have the sigma square dependence, right, in the loop. We fixed it in the loop, uh, finding that this didn't really affect constraints. But yeah, in principle, this dependence is there. Yeah, yeah. So yeah, we used n equals 8 just because PT challenge is huge. But if you use n equals 4, you can also still get, right, if you look at the bottom panel, I mean, the monopole, you can still get at better than 1% with just 4 of these things. So this is going to be very efficient. I should say that we use the FFT log, the existing pipeline, to compute these bispectrum tensors. So these SIJK, which are the spectrum integrals with the basis functions. We used FFT log for that just because it was easy to do and this pipeline already existed, but it's not really necessary. It's still convenient though, because there are also binning effects that we need to worry about. This is very complicated for such a huge volume, right? We need to actually integrate the bispectrum loop over the K bin, right? So there's a finite width and there's the angle integrals, et cetera, et cetera. Yeah, this is complicated. Yeah, so then in the end, if you would use n equals 8, then you evaluate the one loop bispectrum in a little bit less than a second. And if you use n equals 4, then I mean, it just scales cubically, right? Because this is cubic. Sorry? Yeah, like 300 triangles or something. Yeah. And fully integrated over the blah. Yeah. We didn't test it explicitly in this paper. Yeah, it could be that if one uses a different prescription, I mean, of course, there are going to be differences, but to what extent they are reabsorbed by the nuisance parameters in the bispec, I don't have a concrete answer to that. Sorry? Oh, you mean, yeah, sure, yeah. Yeah. Yeah, I understand. Yeah. Um, it could be. I mean, we did it in the loop because we can. I mean, at least in this approximate sense, where we, treat the cosmology dependence in some trivial way. But yeah, it could be that it wasn't needed. We didn't check. Um, yeah. I mean, that K of 0.2 is like, yeah, I get. Yeah. Yeah, so okay, you can fit PT challenge by spectrum. That's a nice thing. So we compared the tree level bispectrum monopole to the one loop at several different wave numbers. And all of this, by the way, this is in combination with the 2-point statistics already, right? So um, in Misha's pipeline, he uses this the power spectrum monopole and quadrupole up to something like Kmax of 0.15. And then in some slightly higher wave numbers, you also have this real space statistic, this Q naught. Yeah, I didn't want to go too much into that, but at least this is already combined with 2-point, right? All the contours that you see are combined with 2-point. So yeah, the tree level is the gray contour. I will show you a zoomed in plot in a little bit. But this one is just to show, at K of 0.15, which is the blue one, we are happy with cosmological constraints. And then at Kmax 0.17, 0.20, this is not good. In the sense that, we're not just off of the cosmological parameters, but also, you can see for the yellow one, for example, you get like a 5% or so bias in sigma 8, which, is completely wrong in PT challenge, but it would also be wrong for, you know, current surveys, like DESI, 5% you cannot tolerate. Right. Uh, okay, so then the other thing that we did is we rescaled to DESI year 5 volume, which we took to be 20. Of course, it's not completely realistic. Sorry, Merda. Oh, so it's not completely realistic because you have multiple redshift bins and so on and so forth, but just to get an idea. Yeah, this is mainly to check how large or good or bad prior volume effects are with this very large number of nuisance parameters. Yeah. So the redshift we analyze is 0.61. So these are these LRG like mocks. Yeah, it's 0.61. Yeah. Yeah, you can also, right, but we only did one redshift. Yeah. Um, okay, mhm, right. Um, yeah, I don't have an immediate answer to that. Okay, let me think about it. Um, yeah, because I mean, you just rescale the covariance to match the C volume is this 500. Yeah, yeah. Yeah, exactly. So I mean, the idea is we control theoretical errors, right, by having some huge volume. The same you would do with Abacus. If you fit the full 200, then you can really see like what fraction of a sigma you have under control. So that's the idea, right? PT Challenge also does that. Yeah. Right. So just to flash you the priors that we put in this case, I mean they are all, let's say, um, they are informative, but they're also not that tight. Of course, this can be contested always, but just to show you the priors that we put, and it seems that this gray contour um, is not subject to huge prior volume effects. But okay, this needs to be studied in more depth. But really, the thing I want to address here is just the fact that you can run these chains and get no theory error for the one-loop bispectrum. That's really the important part. Right. So maybe some more details. We added some new counter term contributions that Misha found, which you get if you take these mixed stochastic terms, but then you evaluate the power spectrum to one loop order. Apparently, these were not included in the previous works. And yeah, they seem to matter a little bit, but also not a huge difference. And we get unbiased cosmology up to a max of 0.15 for the bispectrum monopole, again in combination with the 2 points. And then we were also able to add the bispectrum quadrupole and hexadecapole with a slightly lower Kmax. Again, not super surprising. And then you can see, for example, right, that the red, which combines these three, I mean, is considerably better than the tree-level bispectrum. And yeah, if you then work out what the numbers are, you get roughly a 2 times increase in survey volume. So it seems to be adding some information, right? Yeah. No, it has a free parameter. Yeah, but it's just, I mean, we put Poisson prior on it, right? So you just have like this P1 loop thing. And yeah. Yeah. Oh, Okay, so the power counting argument that we had, right? Okay, maybe you discussed this with Misha already, but uh-huh. Sure. Yeah, yeah, yeah. Oh yeah, 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 yeah. Yeah, 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 yeah. Yeah. Um, but yeah, I mean, to get these things to work, I mean, hacks are needed for PT challenge, right? For the full volume because you have to deal with these binning effects, et cetera, et cetera. So um, yeah, it's the point is just that the contour is smaller than the tree level one. Um, okay, so another thing I should say is that there were some shifts in second order bias parameters when including the one loop bispectrum. It's not really clear where they come from, at least to me, but the significance is low when rescaled to the DESI error bar. And yeah, maybe something to be discussed as well. It's not really clear to me what is the consensus on what to do when these counter terms, well, when these bias parameters somehow become scale dependent to some extent. It's not really clear to me in DESI, for example, how or if this is taken into account. Um, sorry? Well, I mean, in terms of the DESI error, it's like it's less than a sigma. So, you know, you plot it as a function of Kmax and you see like a sigma shift or so. I mean, it looks very dramatic in the full volume, right? But then it's not clear what sort of threshold people should or should not use. So, um, yeah, yeah. Uh, so I mean, when PT Challenge was initially carried out, and that's when it was blind. I was not part of this, right? But um, it was blind, and that was only power spectrum analysis, right? So then, I mean, once they did that, they knew the answer, right? There's no avoiding that. And so then, when you add the bispectrum, um, I don't think it would be possible to do that in a fully blinded way, or at least I think that would be very hard because of, you know, errors that have not so much to do, I think, with EFT by itself, which is what I'm trying to, but you know, more things like binning effects. These are very difficult to control at large volumes. Um, yeah, but so yeah, I mean, it's not to say. So when I say no theory error, okay, what I meant is, and maybe I should have used different wording, but what I meant is that um, whatever theory prediction you write down, you can compute in feasible amount of time without adding an error on top of that. Okay, so maybe I could call that emulation error or something like that. But I'm talking about purely numerical thing, right? Here, okay, we also get unbiased constraints at this Kmax. Of course, you can contest, you know, these error bars are extremely small. Am I not just fitting something that I shouldn't be fitting? Are there systematics in the simulation, so on and so forth? Um, yeah, yeah. Well, then maybe no, no, but yeah, 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 sure, sure. But okay, thanks. Um, So how much time? Mark, help me. Oh, okay. Yeah, so in the next or in the remaining part of the talk, I would like to talk about the matter power spectrum at next to leading order, which we then also did with this method. So for this case, there are no fancy analytics available despite some partial results by, for example, Zach Slepian has a paper on computing two-loop integrals, and also in Marco's older paper, there's some expression in terms of hypergeometric functions, but not at the level where you can actually go and compute the two-loop power spectrum. There was some discussion in Matt's talk about these counter terms in the two-loop matter power spectrum. All I will just say here is that we use the 4-parameter prescription for the matter power spectrum at 2 loops, where you have counter terms like CS squared, right? That's a 1-loop counter term, and then at 2 loops you will have k squared p1 loop. Then there is a quadratic counter term, right, from k squared delta squared. And then you also have a k to the 4 bilinear. So we don't include k to the 4 by itself. Yeah, I think if I'm not mistaken, this is also where Matt and collaborators concluded that these are basically the counter terms that you can meaningfully constrain. And the other ones more complicated. Okay, so then we checked that this set of counter terms basically takes into account all the lambda dependence. That's what you see in the plot on the right. So that's good. And okay, then in view of time, I'm also going to skip this. I just want to say maybe briefly that if you want to compute now these tensors that you need for the 2 loops, I mean, you can do a counting argument saying, okay, let's say I use n basis functions and I want to populate this symmetric tensor of rank 3. That means you only need 56 integrals to pre-compute. And you can do that in some nice combinatorial way where you don't need to make any changes to code that you have for the 2-loop power spectrum already. Like, that's nice, but let me just skip that. But basically the point is you need relatively little pre-computation. So then we went up to n equals 9. So 9 basis functions for the 2-loop SPT piece, which is the most expensive bit, right? And we used 80 k-bins between 0.01 and 1. They're log spaced, and then we oversample between 0.05 and 0.5 a bit, just because there's more features there. And you recover the full power spectrum. So that's the plot on the right to, let's say, per mil accuracy. You need fewer basis functions for the no wiggle part of the integrals, right? So where you just integrate the smoothed power spectrum. And you can see in the plot on the left that, yeah, we reach already, you know, this is the 95% error. So you can see that we already reach sort of per mil or so with n equals 9 on the 2 loop. And this spike that you see is just because the 2 loop crosses 0. Okay, so this is nothing to actually worry about. Right, then we see that when we then compute the error on the total power spectrum, you get the plot on the right. And so what we did here is, of course, we don't know what these counter terms are. So to get you know, reasonable values for these counter terms, we just fit them to some given template for the nonlinear matter power spectrum. Again, just to get reasonable numerical values for the counter terms. And then, yeah, that's how we determine the total error. We did it for 2 different choices of Kmax, but yeah, just to show that really on the total, you can expect per mil precision, let's say. Yeah, then you evaluate the total 2-loop EFT power spectrum. That takes you 1 millisecond because, again, all these tensors are now very small. And it means you can run a chain. So yeah, when we ran the chain, I'm running a bit out of time, unfortunately, but what we try to do is we try to replicate the results from an older paper by Simon Foreman, which used this dark sky simulation. Again, this has a huge volume because it has 8 gigaparsecs on a side. And then we just rescale the volume to something more reasonable, like the DESI one. And now we're able to run an MCMC on the matter power spectrum with the Tulip EFT model, when, for example, consistently marginalizing over the baryon density and the spectral slope, as you would also do in, normal full shape analyses. So, right, these priors, they're kind of very similar to what DESI has, except the NS prior is uniform. But we compared the one loop EFT model to the two loop EFT model. And then we find that with the two loop EFT model, you can go much further in K-reach. So you can see, for example, this figure of bias metric in the top panel, and also the figure of merit on the 3, standard lambda CDM parameters that you would constrain with full shape. And you see that the two-loop power spectrum does better. We also checked running of the counter terms, but yeah, there was not much to see there. So in the end, just to give you some numbers, if you cut off, and this is at redshift 0, by the way. So yeah, at redshift 0, if you try to fit this with one loop EFT, go up to a little bit more than K of 0.1, and then with the two loop, you go to K of 0.26. This is mainly driven by this figure of bias, which we would like to keep below 1. Of course, we can discuss whether, whether these thresholds are chosen reasonably and so on and so forth. But at least for this, which is our baseline choice, we get this comparison in the MCMC. So the blue is the two loop EFT with Kmax 0.26, and red is Kmax of 0.11 with the one loop. And so you see that, there is some improvement. And for example, the error bar on omega matter shrinks by about 35%. If you look at the figure of merit on the whole thing, it corresponds to roughly, again, doubling the survey volume. However, of course, well, truth be told, as you see in the right plot, when you go to higher Kmax, you're putting a lot of constraining power into these counter terms, right? So you can see that the counter terms, they're much, much better constrained as you increase Kmax, right? The error bar on some of them drops by like a factor of 5 or more. And so it would be nice if we had ways of avoiding that, which is where potentially some of Matthias' recent work could help. But yeah, so this is the result that we got for this comparison. Yeah. Yes, it's shifted, but just because we didn't explicitly subtract that piece from the two loop integrals, right? So that is expected. Okay, so then I think I'm pretty much at the end. So there's been some more work led by Matthias Carney on now generalizing this also to loop galaxy bias. We know how to handle renormalization right now, and yeah, we just need to figure out how many bias parameters we need and how many degeneracies can be removed, etc., etc. But really, the main point that I want to make at the end of this talk is that it is numerically feasible to do this with this COBRA framework, right? Maybe we can reduce the number of basis functions a bit further because currently I'm just basically trying to get a uniformly distributed error on the linear power spectrum. But if I already know that this loop is only sensitive to some wave numbers in particular, which I think you generically expect, then maybe you can do a bit better. And also one thing that I think Matt and collaborators did in some more detail was some numerical preconditioning on the integrals before you compute them by subtracting some UV sensitive parts. So this could also be useful in reducing the pre-computation time. But anyways, it's feasible. Yeah. So yeah, let me just leave my conclusions there. My version of this one loop redshift space power spectrum, this is already available, and then over time I will add also the two-loop power spectrum, for example, and maybe some other things. But yeah, thanks for your attention. Yes. So I don't think we're at that point yet. I think we would first have to see, we would have to have a theory prediction ready, and then, to what extent, um, to what extent it makes sense to apply this. I think also before that, I would like to explore, for example, how many parameters do you have? What sort of priors would you need in order to get meaningful constraints, right? These are things we don't understand yet, and yeah, depending on that, we will apply this to this data, or maybe data has to be better before this kind of this is a very complex thing, right? So I would say we don't know a priori whether this works. Yeah, Dennis. Yes, all of that was in Lambda CDM. Well, the those templates, they are sort of, well, okay, maybe not if you put them into the loops, right? Because you also have FNL loops, but I think um, that those things you can probably compute just fine with FFT log, as long as the template that you have is separable, so just some combinations of powers of k. If you have something more complicated, like I don't know, some feature in the bispectrum, then maybe you could also use things like this. Yeah. 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 Yeah, sure. Hmm. Yeah, right. So I mean, like how you emulate the linear power spectrum. I mean, people have done things that are very similar to what I've just showed. So for example, I think the Bakko emulator, you actually do pretty much this, except the preconditioning is where you take actually the log of the data before normal. But that I cannot do, right? I cannot take the log because I have to preserve linearity if I want to plug it into all these loop integrals. So the point of this part is really to preserve linearity. And then maybe to understand your question, I mean, is yeah. So are you asking, for example, whether you can also just build an emulator directly for the thing and like not care about this? Yeah. Okay. So I mean, I definitely don't want to say that like what I'm doing here is the only way you will ever tackle this problem. I certainly think that would be an overstatement. I will just say that once you have this linear decomposition that I have for the linear power spectrum, everything else in terms of computing any loop is sort of it's practically very straightforward, right? I just have to do all these things. I don't have to worry about, oh, maybe I didn't add enough points and like, oh, the error is bad, whatever. I don't have to think about it once I fix the linear power spectrum. So in that sense, it's convenient. But yeah. Yeah, but I mean, they're very adjacent, I would say. And also another thing is that, I mean, of course, at some point, this also ceases to become useful, right? Like, for example, if I want to compute the 10 loop power spectrum, it doesn't help for me to know that it's like a rank 10 tensor and so on, because then these pre-computations, I would need huge numbers of all these bases. So like that wouldn't make sense. But here, it's a sensible thing to do, right? There's good information in the fact that it's actually like a rank 3 multiple. So yeah. 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 Yeah, yeah, yeah. Yeah, yeah, exactly. Yeah, for bispectrum, yeah. Yeah. Exactly. So I mean, I have not ever explicitly compared this to other approaches. I just want to say that this works very well. And I mean, people can get very clever with neural networks, et cetera, right? So, I mean, for sure, somebody else, can do a valiant attempt, and I would like to see, right? Yeah. Yes. 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 So I think, okay, I should have maybe mentioned that a bit more explicitly because it is based on this evolution mapping approach, right, by Ariel Sanchez and what Alex Eichenmeier then also did in this Comet emulator. Yeah, so the idea is that, and we're using that here to construct these templates in a reasonable manner, right? Because if I have 9 parameters and I want to do this SVD, I mean, doing 10 in every dimension, I would have 10 to the 9 templates. I don't really want to do that. That would be very memory intensive. But if I know that some parameters don't really affect anything other than the amplitude, then I should just fix them. And that guess is based exactly on this evolution mapping approach. So things like W naught, WA, they're fixed. H is fixed. AS, of course, is trivial. And then, yeah, if you only vary the physical densities, then those are the things that affect the shapes, right? Yeah. So yeah, those things are definitely used. Yeah. 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 So that came out after all of this, right? Or I mean, after at least our first paper. But I did. Oh, where do I have? Yeah. So when I generated these templates, I did also vary the neutrino mass, as you can see in the MNU row. But yeah, presumably, if you take these new evolution mapping ideas into account, maybe you can fix it somehow. Um, I will just say that in this extended space, I mean, currently most of the error that I'm getting seems to be coming from my emulation of the weights. But yeah, of course, it's possible that you can also get better compression if you use this evolution mapping approach for neutrinos. Yeah, that could be. Yeah.